The Strait of Hormuz is a narrow, tightly constrained coastal choke point. Because of its geography, naval warfare here operates under entirely different rules than open ocean engagements. The primary threat in these waters doesn't come from massive destroyers. It comes from swarms of small, highly agile, heavily armed fast boats that emerge suddenly from hidden coastal inlets to strike. You might expect the U.S. Air Force to send their newest fifth-generation stealth fighters to handle this, but modern jets fly too fast and too high to effectively track small, erratic surface targets darting through a cluttered coastal environment. To counter this, the A-10 Thunderbolt drops down to a persistent overwatch mission. It can loiter for hours just above the waves, flying low and slow while pilots visually hunt for threats attempting to slip through the strait. Out here, the A-10 operates within a layered tactical network. They work directly alongside Apache attack helicopters to hunt these surface boats and intercept one-way attack drones before they can reach their targets. Looking at this diagram of the A-10's wings, you can see how it achieves this extreme low-speed flight. As the jet slows down, leading-edge slats deploy to manage high-angle airflow, while trailing flaps extend outward to maintain lift. When the pilot needs to drop velocity instantly, massive split-panel air brakes split open, creating a sudden, massive disruption of airflow and intense aerodynamic drag. Dominating modern coastal combat requires mastering the aerodynamic physics of low-speed maneuverability rather than relying on supersonic stealth. Flying this close to the surface exposes the A-10 directly to heavy small arms fire and man-portable air defense systems. A MANPAD is a shoulder-fired surface-to-air missile designed to track and destroy low-flying aircraft. To detect those threats, the A-10 relies on radar warning receivers positioned on the nose, the wingtips, and the tail. These RWR sensors pick up radar signals from enemy targeting systems and create a 360-degree digital shield around the aircraft. When a target lock is detected, the system immediately alerts the pilot and deploys a blinding cloud of extremely hot magnesium flares. These are designed to spoof incoming heat-seeking missiles and throw them off their flight path. This wireframe X-ray reveals the aircraft's defense layer. The A-10 uses thick aluminum alloys, supported by heavy-duty beams running the entire fuselage and wings. This redundant engineering ensures if exterior skin is shredded by flak, the internal structure holds the plane together. The A-10 survives combat not by avoiding enemy detection, but through an engineered frame capable of absorbing and negating catastrophic battle damage. The ultimate physical failsafe sits right at the front of the aircraft. The pilot's cockpit is completely encased in a 1,200-pound solid titanium armor shell, commonly referred to as the bathtub. This heavy plating, combined with thick bulletproof glass, allows the pilot to withstand direct anti-aircraft impacts that would instantly destroy a $100 million stealth fighter. Below that armor, the A-10 utilizes redundant mechanical flight cables. If enemy fire knocks out the primary hydraulic systems, the pilot can physically muscle the control stick to steer the plane using raw mechanical linkage. The military only risks these low-altitude coastal engagements because the pilot is shielded by sheer physical mass. It is a weight penalty a stealth fighter simply cannot carry. The entire airframe was actually built around a single, massive weapon, the GAU-8 Avenger 30mm cannon. The gun utilizes a 7-barrel Gatling design. Dual hydraulic motors producing 77 horsepower spin the cluster at extreme speeds, achieving a staggering fire rate of 3,900 rounds per minute. Behind the gun sits a massive internal drum magazine. It carries over 1,100 massive, armor-piercing, depleted uranium rounds. Looking at this cross-section of the feed system, you can see its complex linkless design. Instead of ejecting spent brass into the air, the heavy, empty casings cycle directly back into the drum as live rounds exit. This enclosed loop serves a critical aerodynamic purpose. By retaining the empty casings, it prevents drastic shifts in the aircraft's center of gravity that would occur if it rapidly dumped all that ammunition weight, keeping the plane perfectly stable. Firing those enormous rounds generates over 10,000 pounds of recoil force. That is actually greater than the 9,000 pounds of maximum thrust produced by one of the A-10's own engines. To manage this, engineers mounted the gun slightly off-center to the port side. This precisely aligns the firing barrel with the aircraft's centerline, balancing the immense recoil and preventing the nose from violently yawing off target. Every element of the A-10 functions as a highly engineered flying shock absorber, built specifically to survive its own extreme ballistic physics. When the cannon isn't enough, the A-10 switches to heavy gravity munitions, like the 500-pound Mark 82 bomb. This diagram shows the green cockpit heads-up display, or HUD. To ensure a precise strike, the pilot must perfectly align the aircraft's velocity vector, a symbol indicating the exact direction the plane is moving, with the computer-calculated weapon fall line. For the actual bombing run, the pilot arcs into a steep, semicircular dive toward the surface, hitting the release button halfway through the maneuver. At the moment of release, the bomb inherits the plane's forward velocity. That immense kinetic energy, paired with an attached GPS guidance kit, glides the 500-pound explosive straight down onto the target. By perfectly combining analog structural resilience with terrifying ballistic physics, the A-10 remains heavily equipped to dominate tight, high-threat environments like the Strait of Hormuz. The Strait of Hormuz is a tight littoral choke point heavily trafficked by global shipping. A littoral choke point is a narrow, heavily congested coastal waterway that restricts naval movement. The primary asymmetric threat in this specific region comes from heavily armed, highly maneuverable fast attack craft. Loiter time and maneuverability supersede the advantages of supersonic speed and radar invisibility. These aircraft do not operate as isolated gunships. They integrate into a layered tactical data network, flying alongside Apache attack helicopters to systematically hunt fast boats and intercept one-way drones. The wing pylons serve as a modular strike platform. Pilots utilize the AGM-65 Maverick, an air-to-ground tactical missile designed for close air support, and Hellfire missiles to strike dynamic, moving targets, while the Hellfire is a guided munition built to destroy heavy armor. The physics of unguided weapon release dictate that a dropped bomb does not fall straight down. Instead, it inherits the forward velocity of the aircraft, gliding in a predictable parabolic arc. Adding a GPS guidance kit to a gravity munition actively corrects this glide path mid-flight, adjusting the trajectory for exact mathematical precision upon impact. Pilots utilize a terrain masking approach vector to deliver these payloads safely. They use low-altitude physical geography to block enemy radar detection right up until the point of munitions release. The A-10 pairs networked real-time battlespace intelligence with the precise kinematic execution of gravity-fed and guided ordnance to dominate close air support. Operating at low altitudes guarantees exposure to intense surface-to-air fire. Surviving those conditions requires extreme structural engineering. The cockpit is encased in a 1,200-pound titanium armor shell, commonly known as the bathtub. This is paired with specialized bulletproof canopy glass to shield the pilot from direct impacts. This extreme physical protection allows commanders to authorize high-risk attack vectors that would cause catastrophic structural failure in standard composite frame jets. Inside that armored shell is the digital architecture required to execute a strike, specifically the Precision Attack Control System, displayed on the pilot's head-up display. This HUD recreation shows the required computation for a strike. The pilot enters a semicircular dive and manually aligns the aircraft's velocity vector against the computer-calculated impact fall line directly over the target. The jet merges heavy physical material science with advanced digital computation. Pilots calculate precise strike mathematics while the airframe actively absorbs heavy anti-aircraft fire. The core kinetic system of the aircraft is the GAU-8 Avenger. The entire aluminum alloy airframe was originally drafted around this massive 30mm rotary cannon. Integrating the weapon required severe structural compromises. The front landing gear had to be pushed to the side, and the gun itself is mounted off-center to the port side. This off-center design is a physical necessity. It directly counteracts the 10,045 pounds of recoil force generated during firing, preventing fatal pitch or yaw deviations during a strafing run. The weapon's hydraulic architecture relies on dual hydraulic motors, producing 77 horsepower to rapidly spin the 7-barrel Gatling mechanism. The sequential rotation of those barrels achieves a fire rate of 3,900 rounds per minute, allowing critical thermal cooling between individual shots. The 30mm ammunition utilizes a depleted uranium penetrator. Depleted uranium is a dense, heavy metal that self-sharpens upon impact, allowing a single round to shear through 38mm of solid steel at a range of 1,000 meters. Firing at that rate introduces a massive engineering hurdle. Ejecting thousands of heavy spent casings would instantly alter the aircraft's center of gravity and risk engine ingestion. This schematic illustrates the internal linkless feed system. It mechanically cycles the spent breaths directly back into the drum magazine to maintain the exact mass balance of the aircraft. The GAU-8 acts as an integrated mechanical ecosystem that dictates the aircraft's entire aerodynamic and mass balance, rather than functioning as a standard attached weapon. Sustaining this heavy payload requires the specific propulsion architecture of the twin TF-34 turbofan engines. Their unorthodox high-mounted placement on the rear fuselage deliberately isolates the intakes. This prevents the ingestion of foreign object debris when operating from damaged or makeshift runways. The thermodynamic cycle of this high-bypass turbofan begins with the fan rotor drawing in ambient air for extreme high and low-pressure compression. During the combustion phase, injected fuel mixes with that compressed air, igniting at 1,000 degrees Celsius to generate a continuous flow of high-energy expanding gas. This gas drives the turbine blades to sustain the cycle before exiting the nozzle to generate forward thrust. This specific engine design yields a critical survivability advantage. It produces significantly cooler, slower-moving exhaust compared to traditional afterburning military jets. This reduced thermal output drastically shrinks the aircraft's infrared signature. That severely degrades the lock-on capabilities of enemy heat-seeking missiles. If an enemy missile does achieve a lock, an active countermeasures network of 360-degree radar warning receivers detects pulse Doppler signals and automatically deploys flares. Pulse Doppler radar is a system that measures target velocity by detecting frequency shifts in returned radio waves. The propulsion systems prioritize thermodynamic stealth and extreme reliability over raw speed, calibrating the jet perfectly for the hazards of close air support. To execute aggressive, low-speed attack maneuvers, the aircraft relies on a distinct set of mechanical control surfaces. The wings utilize trailing-edge flaps to increase surface area for lift, while leading-edge slats manage critical airflow at high angles of attack. This vector graphic shows the A-10's wing dynamics. The trailing edges house distinct panel-splitting air brakes. Deploying these creates massive drag, allowing the jet to transition from high-speed dives to stable loitering speeds. Beneath these surfaces is hidden internal redundancy. Multiple independent, load-bearing beams run the length of the fuselage and wings to prevent the airframe from snapping from a single explosive impact. The flight control and hydraulic lines are physically compartmentalized and separated. A pilot retains maneuverability even if an entire section of the jet is obliterated by enemy fire. The result is a heavily damaged but stable aircraft, capable of successfully withdrawing from a hostile strike zone. The A-10 Thunderbolt remains indispensable because every component, from its titanium core to its thermodynamic thrust, is engineered to survive the mathematics of destruction.